For lecture 2, we are going to focus on covalent bonding. The covalent bonding that you are going to learn for H2 Chem is going to be a lot more in-depth as compared to what you have learned in secondary school. So you might want to pay special attention with regards to the content for lecture 2 and the future lecture 3. Because they are not as straightforward as that you found in ionic bonding and metallic bonding. That is if you found them pretty straightforward. Okay, so right now we're going to look at section 4.1. So if you look at section 4.1, there is this learning objective where the students are required to describe covalent bonding in terms of orbital overlap, and the focus here is that it is limited to S and P orbitals only. So if you're not very clear what S and P orbitals are, you might want to refer back to the lectures on atomic structure. So the prerequisite for doing covalent bonding is that you need to be very familiar with what you have learned under atomic structure. Okay, and this is giving rise to what we call a sigma bond and a pi bond. Okay, so the sigma bond, the sigma is spelled as S-I-G-M-A. The sigma here is the Greek alphabet, and then of course the pi is the Greek alphabet as well. Okay, so over here you need to describe what exactly is sigma bond. Okay, so for bond formation, for covalent bonding, the orbitals of the two atoms must overlap. So this is the key criteria you need to be aware of. They must overlap either what we call head-on. Okay, so the key word here, so let me just highlight this. The head-on overlaps, or the overlap could be what we call side-on. Okay, so head-on overlap will give rise to what we call a sigma bond, and the side-on overlap will give rise to what we call a pi bond. Okay, so you can have head-on overlap either between the s orbital. So for example, given in this case under A, you have the 1s orbital coming together, and when they come together, there is this region of overlap over here. So this region is what we call the region where the two orbitals are overlap, and upon overlap it gives rise to what we call a sigma bond. Okay, for 1s and 2p, a sigma bond could be formed as well, so there's also a region of overlap over here. And then of course for 2p, they can overlap to give you a region of overlap as shown by the drawing over here. Okay, the overlapping region. Okay, so if I'm going to highlight, maybe I shouldn't just draw it like that. So if I'm going to highlight it maybe yellow, so this will be the region of orbital overlap. Okay, so you don't need to shade it, when you try to illustrate, but it will be good to know what exactly do we mean by the region of orbital overlap. What would be a good example of a SS overlap? That would be between two hydrogen atom. Then for a 1s and 2p, that will be a sigma bond between H and F. Okay, so that will be some examples which you can probably give. What about a pi bond? A pi bond is what we call a side-on overlap. So it is not a direct overlap, as you can see from the example given in figure 9a, b, and c. For the side-on overlap, it has to come after the sigma bond has been formed. So because the sigma bond, so for example, a CC double bond. So before the pi bond can be formed, the sigma bond must be formed, so that by virtue of the proximity of the formation of the sigma bond between the two carbon, right, then the p orbital of the carbon will then overlap side on to give rise to what we call a pi bond. So this is pretty important. So it is important for the sigma bond to be formed first before the pi bond is being formed. I think this is something that might not be very clearly reiterated by a lot of maybe sometimes it's not being mentioned directly in books or in lecture notes. So but over here you need to be very clear that before the pi bond is formed, a sigma bond must be formed. Okay, yeah. So then you might be wondering, right, why is there a need to describe a pi bond? Well, because you know that p orbital, there are three types, or not exactly types. The p orbital can orientate themselves along either the x, the y, or the z axis. Yeah, so if the p orbital aligning along the x-axis is being utilized to form the sigma bond, so that will be px. So for example, if in this case, if let's say px is being used to form the sigma bond, then the remaining py and pz can't form sigma bonds anymore with the neighboring atom. So because of that, it has no choice but to form pi bonds. Yeah, so because of the fact that the pi bond is formed from side-on overlap, inevitably it will be a weaker bond as compared to a sigma bond, because a sigma bond involves a direct overlap between the orbitals, whereas the pi bond is formed just because the two p orbital are in relatively close proximity, so that the electron cloud kind of overlap across one another. Yeah, so that is kind of like a simplistic view I can share with you. Although if you understand a little bit more beyond the H2 curriculum, that might help you in further your understanding of chemical bonding. But usually what I share over here is more than sufficient. Yeah. There is also another name given to not name, sorry. There is also another way for you to describe the formation of sigma bond. You can describe, if you don't like the word head-on, you can describe it as end-on overlap. Yeah. So you read certain textbook, they might mention end-on overlap to describe the formation of sigma bonds. Okay. But pi bond in most cases is described as side-on overlap. Okay, so yeah, you need to be familiar with the terms. Yeah, I think what was described over here is what I described earlier on is being reiterated here. The side-on overlap tends to be poorer as compared to a head-on overlap. Yeah, so pi bond is inevitably weaker than a sigma bond. Yeah, so between two atoms, if they form a single bond, then it has to be a sigma bond. You cannot form a pi bond without the formation of a sigma bond. So remember this. I think that was reiterated here. Yeah. In our case, these three bullet points you do not really need to memorize, because if you remember what I said, right, you need to form a sigma bond before you form a pi bond. So anything beyond a sigma bond must be a pi until a triple bond. Yeah. Is it possible to have a quadruple bonds? That is, can you have 4 bonds between two atoms? It is possible, but not within the scope of H2 curriculum. Yeah, and then the fourth bond is not sigma and it's not pi. If you are interested to find out more, okay, so you can read up more beyond what we have in the H2 curriculum. Okay, so we will not discuss anything beyond a triple bond. So right now, we can take a look at exercise 4.1. For A, you're required to state the number of sigma and pi bonds present in a CO2 molecules. This is usually quite a straightforward question, and usually is used as a starter question in very long free response questions. Okay, so you notice that for CO2, it forms a double bond with the carbon, forms 2 double bonds with the oxygen. So because it forms 2 double bonds, the first bond must be a sigma bond. So in this case, it consists of 2 sigma, and then the remaining one must be pi, and therefore 2 pi. Yeah, so remember each double bond, right, must be made up of 1 sigma and 1 pi. So if you multiply that by 2, that will be 2 sigma and 2 pi. Okay, and then for parts B, you're required to draw a diagram to illustrate how the atomic orbitals, keyword here is the atomic orbitals overlapped for each of the following. Sigma bond in hydrogen molecules. Okay, so if I'm going to do this question, then I will simply just draw the 1s. So this will be the 1s. So this is the 1s orbital of hydrogen, and then I need to overlap them. Sorry, my circle is not very nicely drawn. Okay, so actually I can use a shape function here if I want it to be clearer. So this is 1. Okay, so maybe I'll try again. Okay, so I'll have a 1s, okay, and another 1s. Okay, yeah, so maybe I'll draw it. Okay, so this is the two 1s orbitals. So I'm just going to label them as 1s, and 1s. So these are the 1s orbital of H, okay, of H, and then of H. Yeah, and then I'm just going to shade this portion to show that this is actually the portion where they form the head-on overlap, or you can just describe it as end-on overlap. Okay, so that would be more than sufficient. Yeah, okay, so remember to just answer the question according to what is required of you. And then for part 2, pi bond in CO2. So we are only required to show the pi bond. So for CO2, so the simplest example I'm going to use here will be to just illustrate like this. The p orbital, okay, and then overlap side on with another p orbital like this. Okay, then over here I'm just going to shade this portion. And then I'm just going to highlight that this portion is what we call the side-on overlap. Okay, so this side-on overlap leads to the formation of the pi bond. You also need to specify what kind of side-on overlap is it between. So in our case here, because we are dealing with CO2, right? So it's a C double bond O. So we need to be very explicit that it's between the two p orbitals of carbon and that of and the two p orbitals of oxygen. If you want to be even more specific, you can say it's between the two py and the two py. But of course, without any mention of the formation of a sigma bond that is between the x-axis, it's quite difficult to actually bring out the 2py or the 2pz in. So there might not be it might not be necessary for you to highlight that it's actually between the 2py and the 2py. Yeah, because remember that all the axes are arbitrary, so it depends on how you define the axis. Okay, so with that, I think we are done with exercise 4.1, and then for exercise 4, for section 4.2, we are looking at the strength of covalent bonding. So it depends on the extent or the degree of orbital overlap, and then how strongly the electrons in the overlap region are being held by the nuclei. Okay, so in energetics, you will learn what exactly is bond energy. So in short, bond energy is the average amount of energy required to homolytically break a mole of covalent bond in the gaseous states. Yeah, so although in our lecture notes we did not mention homolytic bond breakage, so homolytic means that upon breaking you are forming the radicals. Okay, so maybe it's a bit confusing, so maybe I'll just illustrate it for you to see. Okay, so if I have a hydrogen atom, it has a the electron, the valence electron is in the 1s orbital, and then I have another hydrogen atom. Okay, so the valence electron is also in the 1s orbital. Yeah, when they come together, they form what we call the HH sigma bond. Okay, so normally we will not represent it like this. This is what we call the Dor-and-Cross diagram, which we will get to see in the next section 5. Okay, so normally we just draw it as H dash H. So the dash here means the sigma bond between the two hydrogen atoms. Yeah, but you notice that my arrow direction is from the left to the right. Yeah, so we are aware that bond formation leads to energy being released. Yeah, but this is not the definition of bond energy. Yeah, so remember this. This is okay. What I'm boxing up in green, right? This is not the definition of bond energy. The definition of bond energy is actually like this. So it actually is the reverse. So the HH sigma bond, I apply a certain amount of energy, and then I will end up with the two hydrogen radical. Yeah, so this is the definition of bond energy. Yeah, so remember, this is the amount of energy I need to break one mole of a covalent bond. But I emphasize one thing here, which is not in your lecture notes. This is actually a homolytic bond breakage. Okay, so it means that it leads to the formation of the atoms itself. Why did I use the word homolytic? Okay, homo here means that the electrons, after overcoming the bond, right, they are redistributed equally between the atoms. Yeah, so which means you're forming the atoms. Yeah. Then you might be wondering, so are there other kinds of bond breakage? Yes, there's something called heterolytic bond breakage, where one of the atom don't have any more electrons, the other one have 2 electrons. Yeah, so that is actually a H minus. Yeah, so we'll be discussing more about it in the chapter on energetics, so I don't want to confuse everyone here further. So the word homolytic may or may not, I mean, you could include it in a definition, or if you don't wish to, you do not need to include it in a definition. Okay, so if you, but it's important for you to have a good understanding of what we mean by bond energy. Okay, so if you wish to, you can go to your data booklets. So over here, I'm going to my data booklets. I'm just going to the earlier page, maybe page 48. I'm going to look at some of the bond energy. So the bond energy data can be found after the ionization energy data. So these are what we call homonuclear, meaning that the 2 atoms are the same. So that means that for 1 mole of hydrogen molecules, right, if you apply 436 kilojoules of energy, you're going to end up with 2 moles of hydrogen atoms. So this is the 436 kilojoules per mole. This is what it means. Okay, and over here, you need to be aware that bond energies are all defined as homolytic bond breakage. Yeah, I think it is very important for you to recognize this. Yeah, so we will not say that there are 2 types of bond energy, homo and hetero. There's no such thing. So by bond energies, we really mean homolytic bond breakage. Yeah, that's about it. And then, of course, you can compare the bond strength, and then the larger the bond energy or the greater the bond strength, the stronger the covalent bonds. Okay, the distance is also a consideration, but in general, right, the better the overlap, the shorter the distance between the 2 atoms, and then that will lead on to a stronger covalent bonds. Okay, so over here, I think it's quite clear-cut. Smaller atoms tend to have shorter and stronger bonds. There is an exception here, that is fluorine. Although the fluorine covalent bond is very short, but you notice that the bond energy is a lot weaker as compared to what you expect for such a short bond. And the reason is because due to the short proximity of the fluorine the nucleus, because when they form a bond, the fluorine being a very small atom, right, they have to come close enough for the bond formation to take place. But because of that, you expect the lone pairs of electrons on the non-bonding p orbital, because when fluorine forms a sigma bond, only one of the orbitals is being utilized to form the bond, and then the remaining electrons, lone pairs of electrons, are actually being present as well. So the lone pairs of electrons on the p orbital will actually overlap will repel one another. So the electronic repulsion between the lone pairs, right, leads to a weakening of the covalent bond between the 2 F atoms. So because of that, fluorine has abnormally weak bond energy, and this actually gives rise to some interesting characteristic of fluorine. You might have read before, or maybe if you continue to study H2 Chem, you will recognize that fluorine is actually one of the strongest oxidizing agent known to mankind. And why is that the case? The case is actually due to the weakness in the FF covalent bonds. And as to why a weak FF covalent bond leads to it being a strong oxidizing agent, I think I will not go into details, because a lot of it will be covered in future topics. So I don't think I want to bore you with too much details, because I think the focus here in chemical bonding is really to understand the concepts first. Okay, there's also something known as bond order. So a proxy to bond order is actually the number of covalent bond between atoms, or between a pair of atoms, but this is just a proxy, so I don't think we want to discuss too much. You will learn more about bond order in advanced chemistry, in slightly more advanced chemistry, where you learn about the delocalized molecular orbital theory. Yeah, that will actually make it make your learning a little bit more wholesome. Yeah. I think over here we are looking at multiple bonds. So double bond, of course, stronger than single bond. Triple bond is also stronger than double bond, but you notice that the increase is not a multiple. So for example, a double bond, right, you would expect like the double bond to be 350 times 2, 700 kilojoules per mole, but it becomes 610. You might be wondering why. Well, the reasoning is, remember earlier on we mentioned that pi bond is weaker than sigma bond, right? So a double bond is 1 sigma 1 pi, so you have a strong bond and the pi bond is slightly weaker, so that makes sense. So 610, definitely not 700. Okay, then when you increase it to a CC triple bond, so if you take the difference between 610 and 350, that's about 260. So another pi bond coming in, that's also another 200-ish kilojoules per mole, so that will be about 840. It will not be a similar increase. The increase in strength will not be proportional. Yeah, due to many other reasonings which we will not discuss over in H2 chem. Yeah, so over for a CO bond, right? You notice that a CO single bond is inevitably slightly stronger as compared to a CC single bond, and a CO double bond is significantly stronger, and a CO triple bond is also significantly stronger. Why is that the case? Because polar bonds, they tend to be stronger because they are strengthened by electrostatic attraction. Yeah, so that is a localized model that we are talking about. That is what we are discussing here throughout. Later on, you'll learn that this is known as the valence bond model, or the Lewis structure idea of how you actually draw your Dor-and-Cross diagram in section 5. Yeah, but to truly understand why a polar covalent bond is significantly stronger than a non-polar covalent bond, you need to study the molecular orbital theory, which is not in the H2 curriculum. So if you're interested, you can move on to year JC2, where you can take out a H3 course, and that will introduce you to a little bit more molecular orbital theory. Other than that, for the case of H2, we cannot really go very in-depth in explaining why a polar covalent bond is significantly stronger, except simply by just sharing with you that it is strengthened by electrostatic attraction. So what, then you might be wondering, what is the meaning of that? Okay, but because if you notice, right, a polar covalent bond, let's say a CO, right, it also has a dipole, and the dipole is actually towards oxygen by virtue of the electronegativity difference between oxygen and carbon. Yeah, so not only do they overlap head on and side on, leading to the formation of the double bond, yeah, but the formation also result in the electron density being closer to oxygen, because oxygen is more electronegative, and this actually creates a dipole moment, and it makes the oxygen taking on a partial negative charge, the carbon taking on a partial positive charge. Yeah, so this partial charges strengthens the bond in the simplistic way. Yeah, although this is not a 100% correct explanation, it's just a simplistic way of viewing why a polar bond tends to be a little bit stronger, but it is good enough for H2. Okay, then moving on, a longer bond is weaker. I think we can also understand why, because a longer bond here simply means that the overlap between the orbitals tends to be weaker. So for example, for Hi, the iodine, if I move on to the periodic table, maybe I should just go to the periodic table. If you look at iodine is in period 5. Yeah, so iodine will be using period 5 valence orbital to overlap with the 1s of hydrogen. For HF, you'll be utilizing period 2 orbitals to overlap with the 1s. Yeah, so period 5 valence orbital is inevitably more diffuse as compared to that of a period 2 orbitals. So because the orbital is more diffuse, the hydrogen cannot come close enough for a good overlap. So the overlap tends to be poorer, but it still leads to the formation of the Hi covalent bond. So because of that, the Hi bond is significantly weaker as compared to that of a HF bond. Yeah, so you can verify that by simply going to the data. So I'm just going to show you the data over here. Can you see that HF bond is 562 kilojoules per mole, whereas the Hi bond is 299. Yeah, so that's almost double that of a the HF bond strength is almost double that of a Hi. Okay, yeah, so pretty much that's about it. Usually polar bonds, although they are stronger, but due to the polarity difference, right, each of the end tends to be attracted to reactive reactants. I'm very tempted to use the word electrophile, nucleophile, but I recognize that at this stage or in this juncture, you're not so clear about the terms, so I avoid using more advanced terms to explain. But otherwise, although polar bonds are stronger, but there is a tendency for them to be overcome in quite a number of circumstances when a reactive reagent approaches them. Yeah, but we're going to just discuss more of it in the future, so we avoid looking a lot at chemical reactions when we are dealing with chemical bonding. So it's good to just at this stage have a good understanding of how bonds are formed and to describe the different types of bond formation. Okay, so for N2, very unreactive because there is no electronegativity difference between the two nitrogens, so it's a non-polar bond, and at the same time it's a triple bond, so it's very, very strong. Yeah, so without going further, nitrogen activation is a very important area of research in chemistry. Okay, yeah, so we are at exercise 4.2. So for exercise 4.2, you are required to suggest in terms of orbital overlap why the bond energy of CC bond is less than that of a CC single bond. I think I talked about that before earlier on over at table 5. I think I mentioned that because the CC single bond is simply a sigma bond, whereas that of a pi bond is a sigma and pi. Sigma bonds are stronger because that involve head-on overlap, but pi bond side-on overlap, so the regional overlap is smaller, so it leads to a polar bond. So pi bond is weaker than a sigma bond, so therefore a double bond is not twice the bond energy of a single bond. Yep, so that will be the end of exercise 4.2. And then over here we have some useful information regarding bond length, covalence, and van der Waals radius. I think we kind of mentioned a little bit about this in atomic structure. Yep. So for example, in iodine, it exists as a diatomic molecule. So when we measure the distance between the nuclei of the two bonded iodine, we obtain two different values. The first is actually, if you look at the iodine as one molecule, one entity, right? Okay, so I'm just going to highlight this in red over here. Okay, and then I'm just going to indicate the nucleus. Yep. So the distance between the two nucleus is what we call the bond length, and then half of it is what we'll define as the covalence radius. Okay, and then the adjacent distance between two molecules. Okay, so these are two separate molecules. I'm just going to draw the other one in orange. So this is the other molecule that is adjacent to the other iodine. Yeah, then we know that this is the nucleus, this is the nucleus. So this is also the bond length, and then half of it is what we call the covalent radius. Okay, then if we're going to take a distance between these two molecules, the nucleus between the two molecules, right? This is what we call the van der Waals distance, and then half of it is what we call the van der Waals radius. Yeah, so you might already recall this term being used in atomic structure. So if I'm going to go back to the data booklet under section 5 of the data booklet, right? You notice that the covalence radius actually decreases across the periods from group 3, in this case group 3, actually not just group 3, but you can look at it from lithium and beryllium, but might not be so accurate because for them we are defining the metallic radius. But of course you can, if you just lump them together, you could. Okay, but I think we are just focusing on covalent radius. Okay, so if you are looking at boron all the way to fluorine, you notice that it decreases across the period, and we can easily understood this because if you recall from what you learned under atomic structure, right, effective nuclear charge is approximately equals to nuclear charge minus the screening constant. Yeah, so across the period the screening constant stays relatively constant, but nuclear charge increase across the periods. Yeah, so we expect the effective nuclear charge to increase steadily across the period as well. So because of that, the electrostatic forces of attractions between the nucleus and the valence electrons become stronger across a period. So you expect the single covalent radius to decrease. However, for neon, you notice that it is almost twice as large as that of fluorine. Why is that the case? Because for the case of neon, right, neon does not form any covalent compounds. Yeah, so because of that, for neon, we are only defining the van der Waals radius, and that is the reason why for neon, right, the van der Waals radius is way larger than that of the covalent radius of the neighboring atom, that is fluorine. Yeah, so so over here we have the concluding paragraph. So that explains why the atomic radii increases when you go from group 17 to 18. Yeah, because we are looking at different things. It's like you're comparing between apples and oranges and not between the different brands of oranges. So it's not fair. Okay, so you need to know the reason for the increase, and not just because it increased then you thought that it's something something very unusual happens. It is not because of that, but rather we are looking at different kind of measurements. Not single covalent radius, but van der Waals radius for the case of noble gases. Okay, so with that, we have come to the end of section 4, so we're going to move on to section 5, which is probably one of the most important sections under chemical bonding. This is known as the dots and cross diagram. Yeah, so sometimes when we ask you to draw the dot and cross diagram for something, essentially we are also asking you to draw the Lewis structure, especially for the case of covalent compounds. Okay, so the dot and cross diagram is a way of representing the bonds. Usually is for covalent bonds, but it is also possible for ionic bonds, which we're going to discuss right in section 5.1. So you know that the formation of ionic bond usually involve electron transfer between the metal and the non-metal. So for example, for sodium chloride, sodium having the electronic configuration of 1s2, 2s2, 2p6, 3s1. So it transferred the single electron in 3s orbital to the 3p orbital of chloride. So for chloride is 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so what happens here is that the electron in the 3s orbital is now transferred over to that of the 3p orbital of chlorine. So what you end up here is 3p6. Okay, and of course you do not, in this case, you do not need to write out the electronic configuration. So all you need to do is just to draw the dot and cross diagram. Yeah, so remember that this is a little bit different from secondary school. When the cation is formed, valence electrons are lost, so you do not need to draw the 2s and the 2p subshell. You do not need to draw the electrons in the 2s and 2p subshell in. Yeah, that is a little bit different from secondary school, because if I don't recall wrongly, right, secondary school you are required to draw in those valence electrons from the period 2 or the principal quantum shell 2 electrons. You are not required to do that for H2. Yeah, so you can just leave them empty. Yeah, so for sodium, just empty, magnesium 2, empty as well. Yeah, remember for dot and cross diagram, we tend to represent the electrons from another source in a different format. So you either represent them as dots or cross. Yeah, so in our case here, you represent the electrons from sodium as dots. So in this case, that is why this is a little bit different from the rest. Okay, so I'm just going to highlight in orange, for example. So I'm just going to highlight in orange. So this is different, and then this is different as well. That represent the highlighted dots. Orange dots actually comes from sodium and magnesium respectively. Okay, for exercise 5.1, you are required to draw the dot and cross diagrams for the following ionic compounds. Yeah, so for magnesium oxide, again, it should be quite straightforward, because again, cation, you do not need to draw in anything. So I just put Mg2+, so I just put a bracket 2+. Okay, so for oxide is the one that you need to be a little bit careful. Yeah, so I'm just going to show you one of the easier way to do it. So that is just to pair up the crosses. Okay, and of course over here just put it as dots. Yeah, so that's about it. So this is MgO. Yeah, so for sodium oxide, I think you recognize that there are 2 sodium in total. So that's just 2 Na, and then with a plus charge. Okay, so I'm just going to write it out. So this is plus, and then O2 minus is simply just 1 oxygen. So again, represent with a dot. So cross 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 cross, and then that will be a minus, 2 minus. Yep, and then this is usually followed by a part B. Explain why the oxide of sodium has this formula Na2O. Yeah, so this should be relatively straightforward. Why is it Na2O? So we can look at electronic configuration. So because for sodium is 1s2, 2s2, 2p6, and then I'm just going to write out in orange 3s1. Okay, and then for oxygen is 1s2, 2s2, 2p4. Yep. So how many electrons does sodium need to lose in order for it to gain the octet configuration? So it's only required to lose the electron in the 3s orbital. Yeah, but for the case of oxygen, it needs to gain 2 electrons in its 2p orbitals. So because of that, for every 1 oxygen, I will need 2 sodium to lose its single electrons. Yeah, so in that case, the formula of sodium plus, there must be 2 sodium plus for every 1 oxide. Yeah, so it really depends on how you want to answer this particular question. So the easiest way is to explain the number of electrons lost or gain that is needed in order for octet configuration to be attained. Yeah, so because of that, sodium need to lose 1, oxygen needs to gain 2. So in order to gain 2, I need 1 O2 minus to be interacting with 2 Na plus. Yeah, because for every 1 oxygen, I will need 2 sodium in order for the electrons from each of the sodium to be gained by the sole oxygen atom. Yep. Okay, so that will be part B. Right. You notice that the sections at 5.1 is relatively short. Yeah, so that is deliberate because the drawing of dot and cross diagram, right? It's usually more important, if not a lot more important, for covalent compounds. Yeah, so for ionic compound, it's not so crucial because the answer is pretty straightforward. It is the drawing of the dot and cross diagram for covalent compound, especially single covalent compounds, right, that allows us to maybe decide what is the best structure for the compound, or otherwise I think later on you'll be introduced to something known as a Lewis structure. Okay, yeah. So over here we have figure 14, the dot and cross for hydrogen, oxygen and nitrogen molecules. Do note that these are molecules, elements. They are not compounds, because compounds by definition have more than one unique type of atoms. Okay, so for hydrogen we represent the dot and cross. Over here you notice that we alternate between the dot and crosses. The reason is because we just want to differentiate them, but when you move on to university, this is not a requirement, but just for the case of H2 Chem, remember to alternate between the dots and crosses. Yeah, so do remember that you are only required to use dot and crosses. Do not use things like circles or triangles unless the question requires you to do so, or unless the question gives you the permission to use something that is entirely different. Okay, yeah, so I probably do not need to go a lot into details, except that for period 2 elements, you need to check whether an octet configuration is being obtained for that particular atoms. Okay, so we'll try out for exercise 5.2, and then you get a taste of how to actually draw the dot and cross diagram. Okay, so for hydrogen and chlorine, so chlorine, okay, so I'll just look at the periodic table. So just go right straight to the end. Okay, so we are looking at hydrogen over here, and of course chlorine. Chlorine is group 17, so 7 valence electrons. So we have hydrogen with a dot, and then of course chlorine is a cross. Okay, so we'll just try it out first. Cross, 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 cross. Yeah, so you know that chlorine having an odd number of electrons, 7 in total. So you need to share maybe 1 electrons in order for it to gain or attain a octet configuration. And then hydrogen is a duplet. So this will be the simplest dot and cross diagram for HCl. Okay, then for the case of CO2, I think we have the answer above, because in the earlier section, you are required to draw the sigma and pi bond for CO2. So in our case here, it will be pretty straightforward. So carbon will be in the middle, oxygen at the side. Okay, and you know that carbon has 4 valence electrons, oxygen has 6. So the easiest way is to focus on oxygen first. So in order for oxygen to attain the octet configuration, it will need to share 2 of its electrons with carbon, because in the process of sharing 2 of its electrons with carbon, carbon will share another 2. So in that case, if you do a quick count, 2, 4, 6, 8. So that's a total of 8 electrons around oxygen. Yeah, so because of that, we're just going to repeat it to the oxygen on the left, and then that's it. Yeah, so this will be the dot and cross diagram for CO2. Yeah, do take note that for period 2 elements, we are only looking at a maximum of 8 electrons in its outermost shell. It can't have more than 8. Yeah, so this is pretty much similar to what you learned in secondary school. Okay, so do remember that. For CH4, again, hydrogen requires a duplex, carbon 1s2, 2s2, 2p2, so it needs 4 valence, or rather 4 electrons in order for it to attain the noble gas configuration. Yeah, you can actually check it out quite readily over here. So carbon is here, so carbon has 4 valence electrons. Oh, sorry, carbon is actually here, so it has 4 valence electrons. So you will need 4 valence electrons in order for it to attain the neon configuration. So because of that, it will share electrons with hydrogen. So we'll just draw that in. So that's dot and cross, dot and cross, dot and cross, dot and cross. Yep. So that's about it. CH4, pretty straightforward. Okay. There are exceptions to the octet rule, as the octet rule is based on empirical observations. Yep, so if you recall from what you have learned in secondary school, most of the simple covalent compounds you deal with are largely related to the second period elements. So if I can point you to the periodic table, we are dealing largely with the period 2 elements, and you also notice that the secondary school framework for teaching of chemistry in terms of chemical bonding, right, focus largely on selected elements that follow the octet rule quite well. So for example, let's take a look at these few elements that are being highlighted in your notes. Okay, so I'm just going to highlight them. So we have carbon, nitrogen, oxygen, fluorine. Okay, so these are the elements, and most of the time, if you try to recall what you learned in secondary school, we deals with their hydrides. So that means that, for example, for carbon, we deals with CH4. Nitrogen, we deal with ammonia, so that's NH3. Oxygen, we deal with H2O, and then of course, fluorine, we deal with HF. It's quite easy to do a quick count, and you will be able to see that the central atom, in this case carbon, nitrogen, oxygen and fluorine, has the octet configuration, or the neon noble gas configuration. So for example, carbon has 4 valence electrons, nitrogen has 3, oxygen 2, fluorine 1. So when they share electrons with the respective number of hydrogens, so for carbon will be 4, nitrogen 3, oxygen 2, fluorine 1, you'll notice that when they share electrons and form single covalent bonds, the total number of electrons around the central atom is 8. Yeah, so very, very neatly, whatever we learn in secondary school, it seems to fall very nicely with the octet framework. And one other example that you are familiar with includes CO2, the example given in exercise 5.2. So CO2 falls very nicely into the framework as well, because carbon has 4 valence electrons, oxygen 6. So in order for oxygen and carbon to have the octet configuration, each atom will have to share with one another 2 pairs of electrons. So in that sense, you form a double bond each, and oxygen and carbon will have the octet configuration. So that's pretty straightforward, and everything falls in very nicely what you learned in secondary school. Okay, but for A levels, it's not that straightforward, because there are quite a lot of simple covalent compounds that do not fall within the domains of having the octet configuration. The reason being, it's simply not possible. So for example, for the first bullet point, we deal with molecules where the central atom has fewer than 8 electrons. So over here we are dealing with two elements, beryllium and boron. So if you take a look at the periodic table, so for beryllium we are looking at group 2, and boron we are looking at group 13. Yeah, so most of us, when we look at group 2 and group 13, immediately we will think of them being so-called metal. Yeah, so you will think that for beryllium dichloride, it should be ionic in nature. For boron trifluoride, it should be ionic in nature as well. But truth to be told, these elements, right, they have pretty high electronegativity value as a metal. Yeah, so they behave or they exhibit more covalent character as compared to ionic character. Yeah, so in that sense, beryllium dichloride is and boron trifluoride, they are indeed covalent compounds. So if you try to draw a Dor-and-Cross diagram for the both of them, right, you'll notice that the beryllium center has only 4 electrons around it. So if you do a quick count, that's 2, 4. If you do a quick count around the boron center, that's 2, 4, 6, so 6 electrons. So for BF3, it's 2 electron shots from the ideal octet configuration. For beryllium dichloride, 4 electron shots from the ideal octet configuration. So in that sense, we term the boron and beryllium center as electron deficient. Yeah, so in this case we say that they are electron deficient, and in the words of Lewis acid base, we say that they are Lewis acidic. Yeah, in the language of coordination chemistry, we say that they are coordinationally unsaturated. Yeah, but these are just terms or different ways of saying that, you know, the number of electrons, the number of electrons the central atom is lack off from the octet configuration. Yeah, so another question that most of the students will have in mind is, in that case, how are they going to be stabilized? Yeah, so I mean that's probably a very common questions you might have, like if I have them in the as a molecule, as a molecular system, it is unlikely that they are going to be stable. Yeah, so you are not wrong, but over here, right, we do not quite say directly that they exist as a molecular entity. Yeah, so they are stabilized through different ways, which later on we're going to describe to you. So for example, beryllium dichloride will exist as a polymeric form. Yeah, because each of the chlorine will donate its pair of electrons to a beryllium center to stabilize it. Yeah, so but we'll deal with it later on. And then for boron trifluoride, it is likely to exist as a dimer. Yeah, so in that sense, it's going to be more stabilized. Okay, so I'm just going to illustrate the beryllium trifluoride so that it's easier for all of you to understand what I'm trying to say. So for beryllium trifluoride, if you draw the Lewis structure, or otherwise known as the structural formula, it will look like this. Okay, BF3. Yeah, but if I'm going to shift my this fluorine up a little bit to give me a little bit of space, and then I deliberately draw in another BF3, you'll notice something interesting. Okay, so I'm just going to draw in another BF3 here. Okay, you will notice that the fluorine contains lone pair, and this fluorine could potentially forms a covalent bond with the boron center, and this fluorine can also form a covalent bond with the boron center as well. Yeah, this kind of covalent bond is unlike the usual covalent bond you deal with in exercise 5.2. Yeah, in this case, the lone pairs of electrons is the sole contributor to the covalent bonding. Yeah, so this is known as a dative covalent bond or a coordinate bond that you will be introduced later on. Yeah, so I drew it in green here. So the arrow here means that the lone pairs of fluorine donates to the boron center, and in the process, or in this way, right, boron will be able to attain a octet configuration. Yeah, so it makes both boron happy. So my challenge to you would be, could you draw something similar for beryllium dichloride? Maybe not in terms of a dimer, but maybe in terms of a polymer, and then explain, or probably you can highlight why does it prefer to be in that particular arrangement rather than a dimer, or rather than existing as a single molecule. Yeah, so these are some of the things you can think about. And at this juncture, you might be thinking that, wow, chemical bonding, especially covalent bonding, is getting a little bit challenging. Yes, I can agree with you on that, because covalent bonding is usually not very intuitive for most students at the beginning. And if you recall from the very beginning of lecture 1, I did mention that give yourself a few months to understand every single aspect of covalent bonding, and then when you move on to JC2, your life will be simpler, or will be easier. Okay, so right now let's take a look at exercise 5.3. We're supposed to draw the dots and cross diagrams for the following molecules. So AlCl3, aluminium chloride. So again, dot and cross diagram. Aluminium is in group 13. So okay, so over here we have aluminium here, and then we have a dots, so cross, and then Cl, cross, 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 cross. Okay, so we'll do the same thing. Cl, cross, 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 and then dots, cross, and then Cl, cross, 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 cross. Yep. So you'll notice that aluminium is also unsaturated, or in the earlier language we say that it's electron deficient. Yeah, so this is the term to use. Indeed, it is 2 electron shots from the ideal octet configuration, and if given a choice, it will exist as a dimer similar to boron trifluoride. Okay, yeah. Then what about boron hydride? Okay, so same story. We look at boron over here. So group 13, and you know that boron, beryllium prefers to form simple covalent compounds. Okay, so in this case, I'm just going to have a boron over here, and then again dot cross, and then H, cross dots, H, and then cross dots and H. Okay, yep. So I think that's fine, and with that, we'll move on to the next portion. The next bullet points that says molecule whose central atom has more than 8 electrons around it. Yeah, why is that possible? A simple reason we can discuss here is that for period 3 element, remember in atomic structure, we say that when we have principal quantum shell 1, there's only one type of subshell, that is S. Principal quantum shell 2, you have 2 types of subshells, S and P. So over here we have S and P, so we have 2S and 2P. What about principal quantum shell 3? So we'll have 3S, 3P, and 3D. So you'll notice that technically speaking, right, I can have up to 18 electrons for period 3 elements. How did we come up with the magic number 18? Because the maximum number of electrons S subshells can have is 2. P subshells will be 2 times 3, because there are 3 sets of P orbital, or P orbitals have 3 orientation, X, Y, and Z. So that's 6. So 2 plus 6 will be 8. But D subshells we have 5 types. So 5 times 2 is 10. So 10 plus 8 is 18. Yeah. So the maximum number of electrons that a period 3 elements and beyond can hold will be 18. Yeah. So that's something that you need to have at the back of your mind. And that's why over here, the explanation provided is that due to the presence of d orbitals, and then we normally say that it is energetically accessible, octet expansion is possible. Okay, now I don't quite like this term octet expansion because it just sounds weird. It simply means that it can hold more than 8 electrons in its outermost shell. But this is not something that is very, very unusual, because as we mentioned earlier on, the fact that the 3D orbitals are available or energetically accessible will mean that it is possible for us to have more than 8 electrons in its outermost shell. So it shouldn't be like exceptions or something. It's probably more like a norm, like, because saying that it's an exception is not entirely correct. Yeah, because the truth is having 3D subshell allows for octet expansion. Okay, yeah, so PCl5 is a typical example. So if you do a quick count, there are 10 electrons around phosphorus center, so that's fine. Okay, yeah, so over here we have a paragraph saying that period 2 elements have only 4 orbitals, so that's S and then 3 sets of P, so Px, Py, Pz, so octet expansion is not possible. What is the next available orbitals for period 2 elements? The next available one after neon, right, is actually 3s, but 3s in terms of energy, it's too high up. So even if octet expansion is so-called possible, that bond will be very, very unstable in that sense. Yeah, so therefore usually for period 2 elements, it is a strict no-no for octet expansion. Okay, yeah, so usually I think to put things simply, for period 3 if you want to have octet expansion, or if you want to have more than 8 electrons in your outermost shell, just make sure that your central atom is not a period 2 element. Yeah, so usually that will suffice. Okay, yeah. Let's take a look at exercise 5.4. Might be easier to discuss it over here. It's a work example. So we have oxygen sulfur group 16. Oxygen forms OF2 but not OF4 or OF6, but sulfur it's possible to do that. So again, same reasoning. Because oxygen group 16 over here and sulfur, 6 valence electrons. So I'm just going to put it down here. 6 valence electrons for oxygen and sulfur. Yeah, so that means that having 6 valence electron, right, in order for oxygen to have the octet configuration, it will need to form 2 single bonds with the fluorine. Okay, so that will mean that if it's going to form a single bond with the fluorine, it will look something like this, OF2. Okay, like this. Yeah, unfortunately, because oxygen is in period 2, it cannot have more than 8 electrons in its outermost shell. Okay, so let me just put in the lone pairs. Yeah, it cannot have more than 8 electrons in its outermost shell. So therefore, octet expansion is not possible. Yeah, because the next energetically accessible orbitals for oxygen will be 3s, which is quite far away or quite different in terms of electronic energy level with that of the period 2 orbitals. Yeah, so octet expansion therefore not possible for OF2. Yeah, so OF4, OF6 will not likely to be formed. But for sulfur, sulfur is in period 3. You can see that it's it's in between phosphorus and chlorine. Yeah, so therefore octet expansion is possible. Yeah, so it's possible for me to have sulfur in the middle, and then after that I can have it's fluorine. Okay, so I have fluorine here, fluorine here, fluorine here, fluorine, fluorine, and fluorine, and then you can just put in the rest of the electron pairs as you wish. Okay, just put in the rest of electron pairs, and then that will complete the dot cross diagram. If you ever need to draw the dot cross diagram, I don't think it's necessary to draw it, but if you just want to try it out, you may try it out. Okay, so you may try to draw SF4. For SF4, there will be a lone pairs of electrons around the sulfur center. Yeah, so the reasoning will be quite similar to what we have above for PCl5. Sulfur being in period 3, it has energetically accessible 3D orbitals to accommodate the extra electrons. Yeah, so therefore for sulfur, it's able to have more than 8 electrons in its outermost shell. Yep. Okay, so with that, okay, it's drawn for you. Okay, I didn't know that it's drawn for you over here. Yeah, so if you wish to, you can draw SF4 as well. Okay, so you're asked to draw a dot and cross for OF2. Anyway, I've drawn it above, so that's fine. State the number of electrons around the sulfur atoms in SF4. So a simple way to do it would be, you know that sulfur contains 6 valence electrons, and then each of the fluorine will form a single bond with the sulfur center, so they will also contribute to the valence electrons around sulfur, so that 6 plus 4 equals to 10. Yeah, so the 10 valence electrons can easily be calculated by simply just adding up the contribution. Okay, yeah, so yeah, besides phosphorus and sulfur, chlorine can also expand octets, etc, etc. So there are a lot of examples, in fact. Yeah, so we do not want to discuss every single thing lah, but I think over here it was mentioned that for chlorine you can form an odd number, I mean you can form bonds with an odd number of fluorine atoms, but not with an even number. The reason being eventually it will result in unpaired valence electrons, And unpaired valence electron here simply means that it's not likely to be very stable, because having an unpaired valence electrons either means that it will behave as a strong oxidizing agent or a weak or a strong reducing agent, because that electrons will tend to be lost, or maybe you'll gain one more electrons to become a negatively charged species. It really depends. Or maybe the presence of that single electrons will result in dimerization with another ClF4 or ClF6 molecules. Yeah, so these are all highly possible. These are just some possibilities that could happen, but we're not saying that in reality they exist. Yeah, because normally when you have a radical, the radical will tend to pair up with another radical to form a single bond, because having a single bond here means that the species is likely to be a little bit more stable. Yeah, okay, then the last bullet point here, we have a molecule with unpaired electrons. How can we decide whether it has unpaired electrons? Well, it's actually pretty straightforward here. Basically, we deal with an odd group. So, for example, group 15 and group 17. Yeah, so if you look at NO, right, nitrogen has a total of 5 valence electrons, oxygen 6. So if you sum them up, the total number of valence electrons is 11. So if you have an odd number, it's not possible to pair them up in such a way that one of the atom or all the atoms have even number of electrons. It's not possible. Yeah, so in this case, between N and O, the preference is being given to N having the unpaired electrons. So usually the less electronegative element will have the unpaired electrons. Yeah, okay, then for ClO2 it's the same story. If you try to just pair them up, you notice that the total number of electrons around chlorine is 7. Then I have 2 oxygen over here, so 2 times 2 is 12. So 7 plus 12 is equals to 19. So this is an odd number. Yeah, so having an odd number here means that the total number, or no matter how I arrange the electrons around chlorine, I will never be able to get an even number. Yeah, so again, between chlorine and oxygen, chlorine being the less electronegative ones, will be the one preferred to take on the unpaired electrons. Yeah, so in this case, chlorine will be the radical. Yeah, and there's a paragraph, there's a line here: species with unpaired electrons, they are called radicals. Radicals tends to be very reactive. Yeah, so we will study more of it later, although not a lot is allocated for H2, but knowing it, there's no harm knowing it. Yeah. So 5.3, we are going to discuss more on the Dor-and-Cross diagram. So several examples are given here. So for example, ethene, polyatomic anions such as sulfates, nitrate, or even ammonium. Yeah, so there are some guidelines. So again, these are guidelines. They do not present the gospel truth. So just read them with a pinch of salt. Remember that they are guidelines, so they just serve as something that you can refer to if you wish to, but they do not represent the situation all the time. Okay, so for example, normally it's mentioned that the central atom is the one with the lower electronegativity. Okay, or the least electronegative one. Usually that's the case. Okay, but for example, H2O, right? O is in the middle. Yeah, so although O is more electronegative. Yeah, so you can easily find out a lot of such exceptions. Yeah. So for polyatomic ions, okay, you can, this rule, if you follow it, usually it works quite wonderfully. Yeah. So for each negative charge, you add 1 electron. The electrons comes from external sources to the more electronegative elements. Yeah, for the positive charge, you remove electrons from the less electronegative element. So for example, ammonium, you remove the electrons from nitrogen. Yeah, so remember to draw a square bracket around the ion and write the charge as a superscript outside the brackets. Yep. Try to make terminal atoms achieving octets. Maybe to put it simply, usually elements such as halogens, oxygen, they prefer octet configuration if they are on the outside. Yeah, hydrogen will prefer duplet. So if you can remember that, that should be fine. Central atoms, usually period 2 will definitely have octet configuration, except nitrogen. Usually nitrogen, if you count the total number of valence electrons, it turns out to be odd, then it will not be able to have the octet configuration. So in that case, nitrogen will have 7 electrons around it. Yeah, then you can consider having a dative covalent bond if it helps in stabilization, but that will come later on. Yeah. Period 3 and above, you can have more than 8 electrons. That should be fine. Usually group 2 and group 13, largely beryllium, boron, aluminium. These are the classic examples that form covalent bonds. They tend to be electron deficient. Nitrogen, chlorine may have unpaired electrons. I think we talked about that earlier on. So unpaired electrons, because they are usually the less electronegative one. So usually they are bonded to oxygen. So therefore they are the one having the unpaired electrons. Yeah. So for exercise 5.5, you're supposed to draw the dot and cross diagram for the following molecules. Okay, so for H2O2, that will be quite straightforward. Remember that there's a unique name here. It's called peroxide. I think peroxide is a term that is worth remembering what it is. Usually anything with a peroxide means that it has an OO single bond. Yeah, so just take note of this. So the name peroxide means that I have an OO single bond. Yeah, so that would be easier for you if you want to try to draw something out from there. Yeah, so for barium peroxide, the clue given to you is that it contains one cation and one anion. Again, barium group 2, but it is not beryllium. So group 2, magnesium onwards, they tend to form ionic compounds. So for barium, same thing. So barium is likely to lose 2 electrons to peroxide. So barium will draw the bracket with a 2 plus. Yeah. So this is actually quite classic. It's quite classic in the sense that I mean, earlier on we talked about how to draw dot and cross for ionic compound, right? So now it's coming back, and we have polyatomic anion, so that is something that is unusual as well. And then for peroxide, if I simply just look at the structure on the left, you notice that I can simply just take this whole thing and then put a -2 charge outside. So I'll do just that. So O, then O will be single bond. So in this case, I'm just going to put it as O cross dots with oxygen here, and then cross, 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 cross. Okay, so these are the native electrons originally belonging to the oxygen. Yeah, if you wish to, you can use a different color. So in this case, 1, 2, 3, 4, 5, 6. I'm going to use orange to represent the electrons that comes from barium. Okay, so just cross and then dot over here. Yeah, so I'm just going to close out the whole thing, and then this is 2 minus. Yeah, so this is a dot and cross diagram for barium peroxide. Okay, sulfate again. It should be quite classic. So the simplest way I can show you is to illustrate it over here. I mean, without looking at the structure, of course. Yeah, so remember, one of the interesting thing about oxygen is that it must have the octet configuration. And in order for oxygen to have octet configuration, it tends to form double bonds. Yeah, so that's something we are aware of. So sulfur having 6 valence electrons will try to do just that. So we'll form double bond with 2 oxygen first. Yeah, because remember SO4 2 minus, right? So that means that the remaining 2 oxygen will have the negative charge, and that means that they will have additional of 1 electrons. Okay, so in that case, I will try to satisfy the oxygen first in order to let it have the octet configuration. And sulfur having 6 valence electrons, 2 valence electrons left. So these 2 must be the one forming the single bond with the remaining oxygen. So this is 1, 2, 3, 4, 5. Yeah, so 1, 2, 3, 4, 5. And then right now I'm going to draw the extra electrons the oxygen gained from. So that's like this and like this. Yeah, so I'm going to put a bracket around the whole thing and then put a 2 minus. So this will be sulfate. Yeah, I think the details are explained over here. If you wish to, you can just read through them. Okay. For PCl4 plus, again, same old story. We put a phosphorus in the middle, and then we put a Cl around it. Remember, it's PCl4 plus, so chlorine is more electronegative than phosphorus. So phosphorus will be the one losing the valence electrons. So phosphorus is in period 3, group 15, so 5 valence electrons, now left with 4 valence. Okay, so just nice. Single bond each with the chlorine. Okay, so I think that makes perfect sense. if we try to draw them out, that will be perfect, because chlorine just need one extra electrons in order to attain the octet configuration. So this is perfect. Yeah, so once I draw that in, remember to put the bracket and then with a plus charge outside. Yeah, so students tend to forget about the plus charge, or students tend to forget about the charge. Yeah, just take note of it. Okay, yeah, so next we have a work example on carbonate. So carbonate, again, is the same old story. Again, we have carbon, oxygen, oxygen, oxygen. Yeah, so CO3 2 minus. So same thing, oxygen prefers to have to form double bond. So again, we try to satisfy the oxygen with a double bond. Okay, but carbon has only 4 valence electrons. Yeah, so again 2 minus, so each of the oxygen will gain an extra electron. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so the extra electrons you'll gain from external sources over here. Okay, so I'm just going to put a bracket 2 minus. Yeah, so that's about it. Okay, of course we need to have the sodium in. So again, the extra electrons from carbonate comes from sodium metal. Okay, what about sodium perchlorate? This is known as sodium perchlorate, Na, or rather sodium hypochlorite. Okay, the name is not so important. Yeah, so that's the cation is actually sodium plus, the anion will be ClO minus. Okay, so we'll just do a quick drawing. So Na is not very inspiring, just Na with square bracket with a plus charge. ClO will be a little bit more interesting, so we just put a bracket first. Okay, so we'll just try to draw something out from here. So again, chlorine will need 1 electrons to have the octet configuration. So because it has 7 valence, so 1, 2, 3, 4, 5, 6, 7. So with a cross here. So oxygen, you notice that it has only 6 valence. So in this case, it is 1 electron short from the ideal octet configuration, but not to worry, because the extra electrons actually comes from sodium. So over here with a cross. Yeah, so overall charge will be minus. Yeah, so this looks quite neat. Okay, of course you hear me talking about it. It seems that it is extremely straightforward. It seems that I can just draw the dot and cross as though everything is, just very easy. It's actually not the case, because in order to draw it like the way I did it, you need to have a lot of experience. You need to have seen enough of these kind of structures in order to get things right. So at this stage, it might be a bit confusing. You might be thinking, how do I know, where, who will take on the extra electrons? Yeah, so whenever in doubt, just go back to some of these guidelines, or you can practice more, because once you are more familiar, everything just comes quite naturally, so not to worry too much. Okay, so for 5.4, we have coordinate bonding, otherwise known as dative covalent bond. This actually satisfies one of the learning objective, which the students are required to describe, including the use of dot and cross diagrams, what exactly is coordinate bonding, and then as in the formation of ammonium and Al2Cl6. So 2 examples you definitely need to know: ammonium and Al2Cl6. Al2Cl6, if you remember, is actually a dimer form of AlCl3. Okay, yeah, so I think earlier on I have sort of described to you what is coordinate bonding. Jumpstart a little bit over here when we discuss the dimeric form of BF3. Okay, so that means that one of the atom contribute both the electrons to the single bond. Yeah, so that's why we draw an arrow from the one that contributes to the one that receives. So fluorine is the one donating the lone pairs of electrons to boron, so we draw an arrow from fluorine to boron. Yeah. Okay, so we'll take a look at what is required of us. So to form coordinate bond, donor atom must have a lone pair. I think everything was mentioned. Valence electron pair not involved in bonding. Yeah, acceptor must have an empty orbital. So why empty? Because you require it to accept the extra pair of electrons. Okay, dot and cross diagram. How do we represent coordinate bonds? We just represent it with either dots and crosses, because it comes from a lone pair. Okay, so in the case of NH3BF3, the lone pair actually comes from nitrogen. So nitrogen is what we call a Lewis basic center because it donates a lone pair of electrons to the boron center, which is otherwise known as the Lewis acidic center. Yeah, so we say that nitrogen is electron rich. Okay, so this is electron rich. Okay, and the boron center is electron deficient. Okay, and then the dot and cross is like this. Remember that both the electrons comes from nitrogen, and then the structure formula or the Lewis structure actually looks something like this. And you can see that the dative covalent bond comes from nitrogen. So the arrow here means that the sigma bond, the electron pair of the sigma bond is solely contributed by the lone pairs of electrons on nitrogen. Okay, then for Al2Cl6 is the same thing. This might look a little bit familiar because earlier on I have shown it for BF3, the dimer of BF3. Yeah, so this actually shows you that the chlorine is the one that donates the lone pairs of electrons towards the Lewis acidic aluminum center. Yep. Then for ammonium cation is the same thing. The lone pairs of electrons is being contributed by nitrogen. Okay, and then a dative bond is being drawn towards H. Okay, so over here I'm just going to show you how the Lewis structure will look like. So like this, H, 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 and then we draw an overall bracket with a plus charge. Okay, yep. Okay, so this should be our final exercise 5.6. Okay, we're supposed to draw the dot and cross diagram for the following molecules, ions or compounds. Yeah, so NO2 is the work example. It's probably the more difficult work example over here. Yeah, so it's drawn for you, so not very inspiring. Okay, so let me just share with everyone the most common mistake showcased by students. The most common mistake showcased by students is the usual thing that they will do, because they remember earlier on that oxygen will prefer to have to share 2 electrons. So in order for the oxygen to have the octet configuration, this is what they will normally do. Okay, dot dot like this. Okay, so this is what normally students will draw, but after they have done this and they submitted, it was being marked. It's being marked as incorrect. Why is that the case? Because there are 9 electrons in the outermost shell of nitrogen, and this is a taboo because nitrogen is in period 2. Yeah, so what was drawn here is not possible. So what do we do? Yeah, so what we can do is to form a dative covalent bond. So we're just going to remove this. We're going to put back the lone pairs here, and that's it. So no choice, nitrogen will have only 7 electrons in its outermost shell. Yeah, and that also explains why NO2, right, having this particular Lewis structure, it tends to form a dimer with another, or rather it tends to form a covalent bond with another NO2 molecule. Yeah, so in this sense, it will dimerize to form something like this. Yeah, because the radical form is not very stable, so when the 2 single electrons come together, they will form a sigma bond, and this is what you get, N2O4. But N2O4 is also not very stable, so this bond is actually extremely weak. So this is I'm just going to highlight in yellow. This is a very weak bond, so it will also simultaneously break to give you back NO2. As to the reasoning, it's not within the scope of chemical bonding to explain it. You probably need to understand a little bit more about the energetics. So probably when you reach the chapter on chemical equilibrium or thermodynamics, you will have a better idea why this is happening. Okay, yeah. So the next molecule we're going to draw is for CO. So again, CO, quite classic, because we all remember that we need to form a double bond with oxygen. But you notice that over here, oxygen is very happy, but carbon is not happy at all, because for carbon, there's only 6 electrons around it. How to get around the problem? To get around a problem, we need to form a dative covalent bond. So we need to erase one of the lone pairs and then put it here. Okay, and therefore the Lewis structure for CO will look something like this. Okay, C dot dots. Okay, and then after that dots. Okay, sorry, Lewis structure. So it will look like this: triple bond, but one of it is actually a dative covalent bond from oxygen, like this. Yep, so this will be the Lewis structure, or the structure formula for CO. Okay, then for ClF4 minus, so we'll try to do the same thing. So Cl right in the middle, and then we have F, we have F, we have F, we have F. Okay, so again, we just form a covalent bond first, like this, and then like this, like this. Okay, and remember that we have a F minus. Okay, so I'll just try to draw the rest first, and then we deal with the F minus. Okay, so the negative charge, or the extra electron, will usually go to the more electronegative element. So in this case, that will be fluorine. Yeah, so in this case, that means that one of the fluorine will exist in this format. So let me just draw it out as a F minus. So again, I'm just going to erase this. I will purposely put this in red so that you know that it actually comes from an external source. Yeah, so in this case, one of the fluorine will form a dative covalent bond with the chlorine center. Yeah, so this is the dative covalent bond that we are talking about. And then the number of lone pairs of electrons around chlorine will be 2 pairs. So 2 lone pairs. Okay, so if you draw the if you try to draw the structure formula or the Lewis structure out, it will look something like this. Okay, it will look Cl, F, 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 and then lone pair, and then lone pair. Okay, and then we're going to put an overcharge that is minus. Yeah, something along this line. But of course, later on you will learn that the actual shape of the polyatomic anion is not like this, but this is not important at this stage. We're just going to draw the Lewis structure out. Okay, and then we have Mg magnesium nitrate. So magnesium nitrate again, Mg2+, not very inspiring, just put that in. And then of course for nitrates, we have overall minus charge. Okay, so we have 2 of this. Yeah, so again, nitrogen center, oxygen, oxygen, oxygen. Yeah, so we try to do the same thing. We try to satisfy the oxygen. Okay, or maybe I'm just going to showcase another way of doing. So one of the oxygen will have the extra electrons. So I'm just going to put it in red. Okay, the extra electrons. Yeah, so because it has the extra electrons, it will only need 1 electrons to form the octet configuration. So I'm just going to draw like this, and like this. Yeah, so nitrogen will be the cross here. So the other oxygen will form a double bond as usual. So I'm just going to draw it in like this. Okay. Yeah, some of you might be thinking, okay, so the remaining oxygen will also form a double bond. But you notice that if it forms a double bond, then the total number of electrons around the nitrogen center will be 10. And this is again a taboo, right? Because it's a taboo to have more than 8 electrons in the outermost shell for period 2 elements. So what do? So we do the same thing. This should be a dative covalent bond from nitrogen. Because of that, nitrogen will have the octet configuration, and the oxygen on the left hand side will also have the octet configuration. Yeah, so this will be the Dor-and-Cross diagram for nitrates. Yeah, so if you want to draw out the structural formula for nitrate, it will look something like this. N, double bond O, dative bond to O with a lone pair, lone pair, lone pair, and then lone pair, lone pair, and then again O, and then lone pair, lone pair, lone pair, and then overall charge minus. You'll notice that I purposely draw all the lone pairs here. Oops, sorry. Purposely draw all the lone pairs over here. So look, so we have the, oops, the thing keeps skipping. Okay, over here. So we have lone pair, 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 lone pair. You might be wondering why I chose to draw out the lone pair. Is to allow you to perform what we call electronic bookkeeping. Yeah, so that you do not have too many electrons around the oxygen center. Because at the initial stage of learning, right, we tend to draw our Dor-and-Cross diagram in a way that does not really help our mind to count electrons around the center. Yeah, so by drawing in the lone pair artificially, sometimes it helps. If you wish to, you can also draw in for the fluorine here. But for fluorine, there isn't really a need to draw in, for a very simple reason. Because if you try to draw in for fluorine, right, you'll notice that it's very it will look very cluttered. And fluorine is quite easy to count because fluorine has only 8 I mean, it only forms a single bond, so it's easier to count. Oops, I noticed a little mistake that I made earlier on. So actually one of the fluorine should have the dative covalent bond because of this. Yeah, so I just recognize it. Yeah, and of course later on, when you learn the next part of it, where you learn the shape around the central atom, you know that ClF4 minus, the shape is not like this. It's actually square planar. So if I can draw out a slightly more accurate version, then you will know what I'm talking about. Okay, so the slightly more accurate version of the answer will look something like this, but again, there isn't a need for you to showcase the shape. Okay, so this will be the slightly more accurate version of the answer. If you want to draw in the lone pairs, you could, so that it will look neater. But of course, too many electrons around it also looks a bit weird. Okay, yep. So with that, I think we are pretty much done with section 5. The next lecture will be looking at section 6 onwards.